So another way for a limit to not exist is for the function to go off to infinity. Let me talk about, specifically I wanted to go back to our first example, right? Because we talked about a lot of things about this, but we just kind of ignored this fact that there's this asymptote there. But you can see if I talk about the behavior of this function at the point x equals 3, if I'm going to the left-hand side, on the left-hand side of x equals 3, it's going down here. It's essentially approaching negative infinity. It's getting very, very, very large and negative. And on this right-hand side, it's approaching positive infinity. So it's getting very large and positive. So we can use that. We can use our limit discussions as well. And we can talk about left and right hand limits in the context of infinity. So limit as x goes to 3 from the left, you'll notice it's getting progressively large and negative. So I would write that the limit equals negative infinity. On the right hand side, I would write that the limit equals positive infinity. And because these two are not the same, again, the same thing applies, that the limit as x goes to 3 does not exist. Okay? Technically, though, these two limits also don't exist because a limit is supposed to be a number, right? It approaches the number L. And here it's not approaching a number, it's growing without bound. So it doesn't exist, but because it's a very specific thing, it's a very specific kind of behavior that it's blowing up, we are going to say that the limit is infinity. What that means is, okay, it doesn't exist, it blows up. Okay? It's an important way to describe what's going on with the function. So now you might ask yourself, all right, I can see that one goes to positive infinity, one goes to negative infinity. Would you ever have a limit where they both go to the same thing and they're both going to infinity? So it's not a one-sided limit, but it's a two-sided limit. And yes, you can. Here, let me just give you another example. If I did, for example, the function, let's call it g of x equals 1 over x squared, this function, of course, blows up at 0, but both sides are blowing up positive because it's x squared, so everything's positive. So in this case, since I can write that the left-hand limit is infinity or grows without bound, and the right-hand limit also grows without bound, I can make the statement that the two-sided limit at 0 is infinity. It's growing without bound. Okay. Yeah. But again, these infinite limits are, it still technically doesn't exist there. We just want to describe it better. So let me kind of give an intuitive definition there. Write it down as a definition for you all. And I'm going to go with the full one first, the way I didn't show it that way, but the way we did with the regular finite limit, with the real limit, we started with limit as x goes to a. So let's write that down. Let f would be a function defined on both sides of x equals a. All right? Except possibly at a itself. I'll go back to that in a second. Then limit as x goes to a of f of x equals infinity means that f of x, that the value, I'll write it properly, the value of f of x grows without bound as x approaches a. Approaches a. From either side. And what I mean specifically by it grows without bound is if we look at our example of 1 over x squared, I can make my f of x as big as I like, right? Let's say I wanted to take f of x to be 1,000, right? So if I wanted it to be 1,000, then what do I need? If this is true, if x squared is 1 over 1,000, so x is 1/10. So if I am at 1/10 or anywhere closer to 1/10, then the value of f of x is going to be bigger than 1,000. So that's the idea. No matter how, and if I want this number much bigger, all I have to do is take my x much, much closer to the point at 0, right? To our point at a. So I can force my function to get as big as I want simply by taking my numbers as close as I need to the point at a. But that a is going to be our vertical asymptote, right? So you can't, well, that's another thing, right? So we're looking at the fact that this function has that behavior of growing without bound. Okay? Now, you do have to, and let me say, you have a little bit careful about this, because we will often say, like for this function, the limit as x goes to 0 of 1 over x squared is infinity. So we use the word, the limit is infinity, and that's perfectly correct to use that word, but you do have to remember that infinity is not a number. So when we use that language, we're being a little bit loosey-goosey, because you can't equal infinity. Infinity is a limit. It's the fact that it's growing without bound, and you're never going to get, there's not a point that is infinity that you're ever going to get there, right? Infinity is always that you can get further. So that's the idea that infinity is a limit. Okay? So, right. And in fact, what ends up happening is that behavior, that it's growing without bound, is, as you guys know, that's what defines an asymptote, right? We think about an asymptote being a point where, say, there's a 0 in the denominator of the function, and that makes it blow up, right? That makes the numbers get very, very large. So it turns out that if we want to properly define what a vertical asymptote actually is, it's going to be that line where that kind of behavior happens. So the line x equals a is a vertical asymptote of f of x if any of the following hold. Okay? And basically that any one of the sided limits is either infinity or negative infinity, or everyone. So if I can say limit, well, let me do it here. Limit the right-hand side is infinity. The left-hand side is infinity. The whole thing is infinity. The right-hand side is negative infinity. The left-hand side is negative infinity, or the whole limit is negative infinity. So, as we saw in our first example, and our second example also was sort of this kind, where we had a closed form, fairly nice function, a nice rational function. We can also define functions in different ways, as we've been seeing. We can define piecewise defined functions. We can make things look really strange. But really, only one of these has to be the case. So, for example, I could define, I'm going to erase this a second. Let's say I'm going to define my function, piecewise function, 3 over x minus 1 for x less than 1, and 2x plus 1 for x greater than or equal to 1. Okay, so I just made that up, right? If I graph this function, you know this guy's going to blow up, and it's going to blow up negative, right? If I put in x equals 0, I get negative 3, so let's just make that there, and let's do this. Right, and it's going to do this, right? So this function is doing that on this side, but on this other side, this is just some normal line. 1, 2, 3, 4, 5. So it's actually starting from 3, right? This is defined. If I put in x equals 1, I've got 3, right? If I put in x equals 2, I have 5, and this line goes like that. Okay, so it's a piecewise defined function. It's something weird, not that weird, but you know, we'll use this stuff all the time. This still is an asymptote, okay, because this function has this limit here. We can see that the limit as x goes to 1 from the left. Now you're going on this piece of this hyperbola, and it's going to blow up negative, right? But if I go from the right, I'm going along this line, bang, and it's just the regular old 3. And in fact, because of the way I define this way, if I put in f of 1, I actually do get 3. I have a point there. So this is a little bit different, right? And it's because we've got a piecewise defined function here. Even though part of it is this other part of this rational function, this other part is just some line, whatever. Anyhow, when you have, a lot of times you guys have had situations where you're like, okay, if there's an asymptote, there's no point. I can't put a point on an asymptote. True. If it's if the whole thing is one whole rational function and that asymptote is just coming from that 0 in the denominator, you can't have that. But here in calculus, we're mixing it up. We're doing these piecewise defined things. They can be weird. It's still a function, see? Doesn't cross itself. Every point has a definition, and this still counts as a vertical asymptote because on the left-hand side, it's going to negative infinity.